All right, let's do this. Let's wrap this up with a discussion of hybrid architectures. This should be the end of this section. So let's go back to the computational theory of mind. Right? We've been thinking about the mind as a computer for a while. The classical approach is one of those, right? Physical symbol systems hypothesis is also using the computer metaphor. In this view, mental processes are kinds of computations, right? They're algorithmic sorts of computations. And what's going on is we're processing information in some way and manipulating in a way to produce the result that we want. So that was the classical view. The question is, what is connectionism? Is it a computational theory of mind? Sort of. There is some algorithmic processing going on, right? Like updating the network, the nodes, the values that connect them, learning rules. But each of the individual algorithms doesn't behave the way the way a computer works. We spent a while talking about representations, so you can see that a connectionist system doesn't represent in a way that where the representations have an effect on the particular algorithm. What's going on is we're changing just the weights between the connections between nodes. So what's good about the computational theory of mind and what's bad about it? Well, there's a bunch of arguments against it. And we'll start with triviality, right? So the triviality argument is when you try to pin down what it means to think about the mind as a computer, sometimes it's really hard to figure out what's at stake. Because we were talking about it in a sort of a step-by-step algorithmic process, but depending on how you describe things, everything is like that. So yeah, the mind is like a computer because everything is like that under certain ways of understanding. We'll come back to that again and again. Computation has limits, right? So Gödel shows us this. We see this with the halting problem. You don't need to understand this, but if you're a mathematician or interested in computer science, you get that there are some fundamental limits to what computers can do. It doesn't seem like our minds do, but actually, for me, it really does seem like our minds genuinely seem like they have more limits than a computer does. I can't remember like pi to 1,000 digits. It's trivial for a computer. We might just be comparing the wrong things. People have argued that embodiment matters, and the computational theory of mind explicitly rejects or ignores it. Same with time, right? As a matter of fact, like a lot of our thoughts happen in the world. They take time, and sometimes how much time you have affects how you think about things, how you process it, what you decide. Computers, well, you've all seen the spinning wheel of death, the little hourglass that just tells you that the computer's going to think about this for eternity. So you have to like reset it. Hopefully our minds never do that. So this is the behavioral shortcomings thing about computers. They never laugh, cry, appreciate art, but we do. And it seems like sometimes we think in ways that are not computational, not algorithmic, just go with our gut in certain ways. Again, like you can represent this as a computer, as a computational thing, but then you go back to the triviality thing, right? Like it seems like when we generalize our metaphor, we actually lose what was so special about it, what it gave us in the first place. And then lastly, the argument that machines can't understand. We spent some time in the translation room. There are alternatives to the computational theory of mind. Some ancient alternatives, some more recent alternatives. Actually, even the situated cognition is fairly ancient. Dynamical models, I think, are more recent. We're gonna come back to this later on in the semester, right? So in the architectures debated section, I've only been talking about 2 kinds of mental architectures, but we're gonna talk about more throughout the semester. I'm just gonna pepper them in because if we spend too long talking about each of these, it can get kind of weary. Whereas when we start talking about different kinds of processing, different kinds of like perception or consciousness or that kind of thing, at a certain point, it's going to make sense to start bringing these in. So we'll do that later on in the semester. Why was anybody motivated to be a connectionist at all? Well, our brains look like connections, really, is the real reason. But lots of other things. Computers don't really behave how humans behave in a lot of ways. A lot of how we experience the world cannot be represented in a verbal programmed type way, the way a computer can, or the way a computer always does. Computers break pretty easily, but humans don't, right? We don't look like, brains don't look the way computers do. Not that that really should matter, right? Like the hardware doesn't need to look like the software, but whatever, I'm getting ahead of myself. So those are the reasons to pursue something like connectionism. But there's arguments against it, right? We spent most of the lesson today on representation. It seems like if we care about representations, maybe we should, connectionism doesn't fit them. So it doesn't reflect how our minds work psychologically. And also, we've oversimplified the biology to such a point that it's actually not how our biology works, right? So massive backpropagation. I know a lot of people actually are pushing for it being more likely than this slide suggests, but it's at least not obvious that that as you make mistakes, you correct every single belief you've ever had. We're ignoring the chemistry, which has got to be making a difference at some point, right? Learning isn't really supervised. We're just associating a bunch of things our entire lives, et cetera, et cetera, et cetera. So you have these 2 approaches, and we're putting them as alternatives to each other. How to we've got certain, in the classical approach, you try to reorient your problems, try to think about how a computer would process certain things. And a connectionist system, you instead try to build a network, try to figure out how complicated for it to be, how many connections to make, what learning systems to use to see how quickly you can solve a particular problem. There's benefits and drawbacks to both, right? The connectionist, oh, this is going to be annoying. I'm sorry, but I'm 9 minutes in and I'm not going to go back. Connectionist is on the left here. It's going to be on the right in the future slides. Sorry. Just be annoyed. So I'll start reading with classicalists. It's classicalist, the computational approach is predictive, systematic, computational. That's what Fodor and Pilishin were arguing. But there's something that's very just descriptive about what's going on. It's restructuring how thought works as how a computer works. It's not really biologically realistic at all. A connectionist system has the ability to withstand interference. It can generalize. It degrades gracefully. It doesn't break. It's not brittle the way classicalist approaches are. But we don't get to capture structured information. Network computation is opaque, and so my network wouldn't be yours. Google can't figure out what Bing is doing, vice versa. Actually, that's a bad example because Bing is copied from Google. Yahoo and Google then. Networks are merely implementation level is the argument here. So we might not have gotten closer to the abstract way of representing how the mind works. And we wanted a fairly abstract approach. All right, now we're switching. Okay, on the left, classicalist, on the right, connectionist. So learning involves hypothesis formation and testing. Representation is local. Degradations break the whole system, right? Some of those are good. The learning, I think, go either way, because learning for connectionists is evolving weights of connections via repeated exposure. On representation, it seems like the classicalist approach makes more sense of our intuition, assuming our intuition of how thoughts work is correct at all. Connectionists can only represent thinking, not thoughts. Nodes are sub-symbols, that is, there's not a single node that means anything. It's the combination that means stuff. But they do degrade gracefully, which is nice. Compositional, sequential versus parallel, common sense versus not. Classicalist approaches can be built pretty quickly, given just a couple of states and rules. Connectionist systems can be trained across infinite. So one of them gets off the ground easier, the other one is broad and can do even inconsistent things. Hard constraints versus soft constraints. Classical approaches are more modular. They're explicitly modular, but connectionist systems can be modular too. We're going to go into modules in a couple of weeks. So we'll leave that there. Can we have both? Would we want to have both? It actually turns out that in a lot of domains of the mind, the classical approach is a very, very, very helpful way of thinking about how your mind works. In other approaches, the connectionist system makes most sense. Can we have both? Well, if we did have both, we could actually divide it in along certain ways, right? So some parts of language would go in both, learning language maybe, comprehension, perception, but the language rules might make more sense in the grammar might make more sense as a computational approach, right? So there might be reasons to have both, or certain aspects of one versus the other, or there could be a handoff in a certain way between how we're thinking about these things, about how the mind works. And if we start thinking about hybrid architectures, we realize that neither of these approaches are explicitly flawed, and in fact, they might be compatible. Different tasks might require different approaches. You can make hybrid models of these, and you can have two very different ways of doing it, right? One would be physically doing it, and the other would just be doing it functionally or implementation versus algorithm, or describe it, have a system in one way, but it can be described in multiple ways. Each of these is going to have issues, right? So if it turns out that vision is modular, but language isn't, you're going to need to figure out how to like interface between your vision and your language. which is a big problem, and actually doesn't bother me that we have problems like that left over. It seems like it should be a problem that we have to wrestle with. Um, so all right, we had very, very different approaches to cognitive architectures, but we kept focusing on particular tasks. And really, a lot of tasks might involve multiple processes, or some processes may be used in many tasks. So maybe we shouldn't be focused on looking for a particular theory of cognition or a particular architecture, but look for architectures or theories of cognition. Keep this in mind as we go on in the semester and we start talking about whether cognition needs to be embodied in some way or dynamic in some way, or the various other models of mental architecture. All right. When we come back with the next week, we'll talk about cognitive neuroscience. Cheers.